Okay, now that we have discussed four different problems, let's try to find a pattern on how to design a DP method. Basically, there are going to be four steps. Step one, characterize an optimal solution. What does it mean? So the key is to define the proper subproblems, and that's usually the hardest part to start with. And then we must check if an optimal solution contains an optimal solution of a subproblem. And step two, recursively define the optimal values. And this is actually the divide and conquer step. That is to find the relationship between the optimal solution of the current problem and the problems with smaller sizes. So to obtain a recurrence equation. All right. Step three, compute the values in some order. That means while we go through the computations, we must be careful. Make sure that while we're calculating this value, everything on the right hand side of the equation have been obtained. And that's what this sum order means. And at meantime, of course, it's safe to start from the smallest case. And the last step is to reconstruct the solving strategy. That is, for example, in the OBST problem, when we're asked not only to find the best total access time, but also to output the optimal tree. We're going to have to reconstruct the tree from our table, and this is what this reconstruct the solving strategy means. All right. Then with these four steps in mind, let's check out another problem and see how these steps are applied. Okay, our last problem is the product assembly problem. Product assembly is 产品组装, right? So we assume that we have two assembly lines for the same car, like this. Okay, we have several parts and we're supposed to assemble them and to produce the final car. And we have two different lines. And along each line, we have several stages. And we use different technology or time for each stage. That means we're actually having a directed graph, right? And on each edge, we have a weight, and that is the time taken to move from one stage to the other. And there's another thing to make this problem a little bit complicated is that one can change lines between stages. We can move from this stage to the next stage, but jump to the other line. All right, and that also costs. And similarly, we can jump from this line to that line with some cost. And our task is to minimize the total assembly time. So what about an exhaustive search? Well, we say the exhaustive search gives exponential time plus a linear cost of the space. The linear cost of space is not avoidable because we have to save those times anyway, right? If there are n stages, it's going to cost us some constant times n spaces to store all those times anyway, right? But the time complexity is the real problem. It's 2 to the power n because for each stage we have two options: take it or not to take it, to be or not to be. And since we have n stages in total, and therefore we have 2 to the power n options. Now let's think about using dynamic programming. Okay, let's try to follow the four steps. Step 1, characterize an optimal solution. So what is a subproblem? Think about this. If this is one optimal solution, and when we check out any stage in between, this path must also be an optimal solution of this subproblem. We can prove by contradiction. If this is not true, so it means that we can reach this stage from some slower path and then still get to this point with the minimum cost. Is it possible? Certainly not, because they share the same last step. And therefore, it means that if this is an optimal solution, then this must be an optimal solution for this subproblem. So here we go. We do have this situation that an optimal solution contains an optimal solution of a subproblem. Okay, so far so good. So what's next? Next, we're supposed to do divide and conquer, right? Recursively define the optimal values. So for any subproblem at any stage, an optimal path to this stage is based on an optimal path to the previous stage, to stage -1. Okay, so suppose this is the stage we're currently looking at, and this is the previous stage, that's the stage -1. So what we have is this. The current cost of this line at this stage can be obtained from the previous stage, from the cost of the same line at the previous stage, that's the optimal solution of the previous stage, plus this process time, which is the process time of this line and from stage -1. That's only one possible way to get to this stage. There's another possibility, right? So another possible way is to jump from the other line, which is what? Which is the optimal solution of stage -1 from the other line. So when this line is 0, we're going to obtain 1. If this line is 1, we're going to obtain 0. So it's flipping from 1 to 0 or from 0 to 1. So that gives the index of the other line, right? So this is the optimal solution from the other line at the previous stage plus the cost of this edge, which is the transit cost, is this cost from the other line and from the previous stage. Okay, so we have two different possible ways to get here. Since we are looking for the minimum solution, we should take the minimum of these two values, right? Okay, so basically we have obtained the recurrence equation here. All right, and to do the computation, the next step is to make sure that we are computing in the right order. What does it mean here? Certainly we're going to start from the initial state, from state 0, right? And well, actually we have two different orders to choose from. One is that we can go through line by line. We first move from stage 0 to this stage with one line and then compute with another line, which means we're going to have two nested for loops, and the outside loop is for line and inside loop is for stage. So when we keep one line, we calculate stage by stage. Then we jump to the other line and repeat the iteration again. Another way to do the iteration is that we set the outer loop to be the loop for the stage. So basically we're updating stage by stage. And for each stage, we're going to calculate for both lines. So which one is the correct order? The second one, right? Because while we're calculating the solution for this line and this stage, we're going to need the optimal solutions from previous stage, but not only for this line, but also from the other line. So we have to know the previous stage from both lines. Therefore, we must iterate for stage first. And then for each stage, we calculate this value for both lines. Well, although it looks like a for loop, but actually there are only 2 steps to go. At the very beginning, we should initialize the optimal solution to be what? To be zeros, right? And what is the final solution? The final solution can be obtained by comparing the solutions at the last stage, right? So the final solution will be the smaller one between these two f of n's from both lines. So what is the time complexity of this DP algorithm? It's linear, right? Because there's actually just one for loop. Okay, and this is a constant, actually, only 2 steps. So within each iteration, there are only 2 steps. Okay, finally, step 4. If we are asked to reconstruct the solving strategy, what do we do? Well, this is basically the same code that we copied from the previous page. The difference is only that we temporarily save the 2 situations here. fStay stores the result we obtained from the same line, and fMove stores the result we obtained from jumping from the other line. And if stay is smaller than move, then we store stay. Otherwise, we store move. So this part is for calculating f. If we are asked to reconstruct the optimal stages, then we need something to record the current stage, right? So here we go. We need another array to store the current line that we have adopted. Okay, if we record stay, we will record this line number. If we jump from the other line, we will record the number of the other line. And actually, these line numbers can be initialized to be anything. It doesn't matter. And this is how we store the plan. So the plan is reconstructed in the reverse order. We start from the endpoint because the final solution is the smaller number between them, right? And whichever is taken, that line number will be recorded into this line. And we start from stage n. The last stage is that line. And then we decrement the stage one by one. So we move from the end point to the start point. And for each stage, the optimal line number is recorded in this array. So we just save them one by one into this plan. And then print this array of plan one by one. And that's reconstruct the solving strategy. All right, to summarize, there are basically 2 key characters that a problem must have to apply DP. That is optimal substructure and overlapping subproblems. To check whether or not you have really understood, let's think about this question. When can we apply dynamic programming? Okay, I would suggest you to pause the video and think about it. Well, there are basically 2 cases, right? The first is that if there is no optimal substructure. Optimal substructure means we can build an optimal solution of the whole problem from those optimal solutions to its subproblems. If that is not the case, then we cannot apply dynamic programming. So for example, if there's a history dependency in this problem, for example, if there is an extra constraint saying that if we take this stage from the first line, then we must not be able to use this stage in the second line. That is called history dependency. If we take the first move to be the second line, then it's okay to use this one. But if we make the first move in this way, even though we can jump to the second line, we are not allowed to use this stage. In this case, dynamic programming would not work because it's possible that even though this pass is faster than this one, this is a slower pass while this is a faster pass. However, there's a much faster pass from this stage to the end. And if we apply dynamic programming at this stage, we must pick up this pass because this is the current optimal solution. However, if we decide to pick up the optimal solution for this stage, we are not going to be able to go through this faster track. And therefore, we're going to be missing the real optimal solution. So this optimal substructure is the first key to apply dynamic programming. And the second point is that if subproblems do not overlap, it becomes sort of pointless. In that case, a direct divide and conquer would be more suitable to solve the problem. So divide and conquer algorithms partition the problem into disjoint subproblems. Well, dynamic programming works when the subproblems overlap. And that is when subproblems share subproblems. If that is not the case, then dynamic programming would not be able to make the situation better. Okay, so here comes your third project. It's about so-called beautiful sequence. So we define a sequence to be beautiful if it contains two neighbors with difference no larger than m. So given an integer sequence with n elements, you're supposed to calculate the number of beautiful subsequences in it. So it's a typical application of dynamic programming. I hope you like it. And from this book of Introduction to Algorithms, you can study more examples.